Okay, so off we go with the fluid mosaic model of a membrane. This is what the membrane of a cell, or the membranes within a cell, are made up of. If we look at the structure of it, the basic structure looks a little bit like this. So you've got little circles across the top, they're called hydrophilic heads, and then you've got little tails hanging down. And the way the tails arrange, they arrange itself in the middle of the actual membrane. Now, if you look to the right, you've got a picture there of a plasma membrane taken with an electron microscope. It's very hard to see what I've got on the left-hand side on the picture on the right. That's why it's called the fluid mosaic model. The model is the idea behind it. So it's not necessarily fact, but it's as close as we can get to modeling what a membrane actually looks like. Now, here it is in all its glory. There's different components that make up a membrane within a cell. Now, this could actually be the membrane inside a cell, a membrane that makes up one of the components, one of the organelles, or it could be the outside membrane of a cell. There are various bits that make up the membrane, which I'll run through now with you. We need to learn what they are, be able to label them, and be able to talk about what they actually do. So first off, number one on the diagram is the phospholipid bilayer. That is the diagram I've just shown you with the heads and the tails in the middle of the membrane. The heads on the outside, sorry, and the tails in the middle of the membrane. The tails are what we call hydrophobic tails. Hydrophobic simply means they don't like water. So they're arranging themselves away from water. We can have some kind of liquid, maybe cytoplasm, on one side of the membrane, and you might have plasma, something in the blood, on the other side. And the tails arrange itself away from that water. Number 3 in the diagram is pointing to the circles, the heads, the hydrophilic heads. And the term hydrophilic simply means water loving or water liking. So the heads always arrange itself nearest to the water, and the tails always arrange itself inside the center of the membrane. Now, as we'll see in a moment, there are channels that run through the membrane, and there's also carriers. So there are two structures that look very, very similar. They do have similar roles, but they are ever so slightly different, and I will talk you through those in a moment. The carbohydrate chain is sticking off the big molecule that is number 7. So a carbohydrate chain is the structure attached to a glycoprotein. Number 8, the carbohydrate chains can also be attached to one of the phospholipids. So in number 8, we call this structure a glycolipid. Simply, glyco refers to the carbohydrate and lipid refers to the phospholipid structure. And finally, number 9, there are components within the membrane called cholesterol. You will have heard of cholesterol before, and I will try and touch on why cholesterol is so important in a moment. Now, each of these different structures within the membrane has got a very, very important role. They're all summarized a little bit later in this video, so you can take your time and work your way through them. But I'll try and give you an overview as to what they're used for, why they're quite important, and where you can maybe try and remember what they are. So first off, structures 1, 2, and 3, in a way, they're all kind of the same thing. They are the phospholipid bilayer, which is made up of 2 phospholipids, and each phospholipid is made up of a head and a tail. The heads will always arrange themselves nearest to water, and the tails will always arrange themselves in the center of the membrane. What that's doing is creating a little kind of waterproof barrier, or as we say in biology, it creates a barrier against polar molecules. So polar molecules are molecules that behave like water. So it's creating a barrier against those molecules. That's what the job of the phospholipid bilayer is. Now, another job it's got is it is stopping molecules that are like water. It's stopping the polar molecules. but it will allow non-polar molecules to pass through. And they are molecules that are like fats. So anything that is like phospholipid, anything that is like a lipid or a fat, can go straight through the membrane. Anything that is polar and is like water can't go through the membrane. Okay, to get anything that is like water, so basically anything that dissolves in water, through a membrane, it has to go through a special structure. So this is where number 4 and number 5 come in. Channel proteins and carrier proteins look very, very similar. They have a very similar role, and they will allow charged polar molecules through. Channels, quite simply, think of it like a channel. They can open and they can close. That's all they can do. And they can open to allow things through, and they can close to stop things from moving. So in a way, you can use your channel proteins to regulate how quickly something can enter a cell or exit from a cell. Number 5 is very, very similar, but you can see on the diagram there, it's kind of a bit wiggly on the inside. It's meant to show that it's moving. Now, carrier proteins kind of move and change shape and push, and they adjust and they squeeze things through the membrane. Sometimes this is by facilitated diffusion, in the same way a channel protein can work, but sometimes it can be used in active transport as well. So that's how we can get polar molecules through structures 4 and 5 on this diagram. Structures 6 and obviously 7, really, they're in a way, they're like little markers that are telling other cells what this cell is. So in a way, it's a little bit like a signal to say, this is the cell that I am. In a very similar way, number 8 is doing the same thing. So these little markers, they're actually what we call antigens a lot of the time. So they can act as antigens. They can show off your cell as being the type of cell it is. So I'm a red blood cell, I'm a nerve cell. And these little carbohydrate chains, together with the glycoproteins and the glycolipids, are what are doing that. Now, they do have extra little roles as well. Glycoproteins can be used to get messages from the outside of a cell to the inside of a cell. But we'll touch on that a little bit later on. And finally, number 9. Number 9 is cholesterol. Cholesterol, you may have heard people talk about cholesterol being bad for you, and it's just so not true. It's like everything. Too much of it or too little of it is bad. You do need cholesterol in your diet. And cholesterol is used in the membrane to regulate how quickly the membrane moves. This is a moving structure. So the cholesterol regulates the stability and the fluidity of the membrane. You want the membranes to be able to flex and move and adjust, but not flex, move and adjust too quickly. You want them to be a nice consistency, and that's what the cholesterol is used for. So here's a summary of everything I've just hopefully covered there. Take your time, work your way through it. Obviously, these are taken from past exam papers, so they're very, very useful to get the kind of key ideas down. And just really, really quickly, here's a structure of a cell. And what I've done, I've just highlighted some of the organelles inside a cell that have membranes. So the structure I've just shown you could be the phospholipid cell membrane on the outside of a cell. This is often called a plasma membrane or a cell surface membrane. The organelles inside, things like mitochondria, Golgi body or Golgi apparatus, they produce structures called vesicles. And some of those vesicles will be excretory vesicles. Some will become specialized and become lysosomes. And some are used in our immune system to fight off pathogens such as bacteria or viruses. We've also got smooth endoplasmic reticulum that has a membrane, and it's sometimes called SER for short. The rough endoplasmic reticulum, again, is made up of a membrane. And then we've also got the nucleus, which more specifically, the nuclear membrane is made up of these little structures. Okay, so it's very important you can label the overall structure of a membrane, talk about what each bit does, but also give some examples of the organelles inside a cell that have membranes. If this was a plant cell, chloroplasts and vacuoles would also have membranes. So again, a little summary there, just kind of telling you which organelles have got membranes. So that's it for the fluid mosaic model of a membrane. Hope it's been some use. Please take your time, revisit the video, pause it when you need to, and make sure you have some really good notes ready to take you through the rest of the year. Okay, take care now. Bye-bye.